to see how these enter into finally into the mass matrix. Because mass, when we discuss mass models, we never talked about electron muon terms separately. We talked about flavors first. But finally, we know that however we generate the masses, finally we are going to observe them at our experiments. We are going to measure the masses, mass per differences, whatever. We are going to measure mixing angles. Maybe CP phases, maybe Dirac phase, maybe Majorana phase, maybe some other phase. So, therefore, the model that we construct should finally give us a mass matrix. And this mass matrix should have certain properties for it to satisfy concurrent data. So that's what we try to do at this. So, yeah, as I said sometime ago, it's basically manipulation of 3x3 matrices. So we'll talk a bit about the structure of Neutrino mass matrix. This 3x3 mass matrix with E, tau, and then we'll see some mass matrices which are consistent with current. So let's first see what we can say about the structure of this Neutrino mass matrix. So what is this? So we will not talk about Dirac mass matrix. The Dirac mass matrix is boring. It is Dirac, because only a Dirac mass, it is exactly like Dirac masses of quarks. And Dirac masses of quarks, people know everything about them from mass matrix. We are very busy. We do the interesting stuff, which is seeing what happens for neutrinos. So Majorana mass matrix, which is a special thing that we do. And we saw that if anything has a Majorana mass, neutrino will have a Majorana mass. So, in all the models that we saw in the last couple of lectures, everything had Majorana mass. Every model knows what a Majorana mass. So, therefore, that part is more important, more interesting. How to write a Majorana mass. So, earlier we have been trying to write things with one flavor. So, with one flavor, what did we write? We said that Majorana mass is given by these terms, minus half some Majorana mass term, mu c bar mu. Okay, you can call it mu n c bar mu or mu 1 c bar mu. Okay, that's a Majorana. Then we knew what mu c looks like. So the mu c bar, for example, mu c bar was by definition minus mu transpose c time. This gets seen sometimes. So let me put this part in, and then the same term becomes half. This is the mass. Mu transpose c dagger. So let's check. I just want to be careful about what these things are. Right now we have only one flavor. There is no mixing, only electronic. Now, what is this transpose then? This transpose is spinor space. There is no flavor space. Spinor space is no Dirac matrices, 4x4 matrices in the spinor space. No smooth indices. Okay. So let me call the indices as some PQRS kind of. So my notation is usually the following. I use PQRS kind of things for spinor indices. Okay. Usually I use PQRS for spinor indices. Then alpha, beta, gamma, delta for Dirac indices. Okay, so space-time indices. And although we won't use it perhaps in the rest of the course, I sometimes use A, B, C. These are sometimes called for distributed indices. Okay, but that's a standard notation that I use, not everyone. Anyway, right now we are interested in the PQRS and alpha. Yeah, sorry. And IJK are flavor indices. Okay, flavor or mass. Electron muon. That is complete. So if I want to write down this precisely, this is is how I write it. Mn is a number. Nu is a matrix. So it's mu p, the p component. It's a vector, yeah. So row, column vector, right? So nu transpose C dagger nu is the same as nu p C dagger p q nu. So this is the qth component. Do you agree with this? It's very important for the next step. So if I want to write down, so this part nu transpose C dagger nu. So nu transpose C dagger nu is simply the short form for this. They are identical. There is no cheating here, no redefinition. It's exactly what definition. That's why you multiply matrices. Okay. Now what we are going to do is we are going to go from one flavor to three flavors. So what will happen? This M will now no longer be a number. It will be a 3 by 3 matrix. And I call it capital S. Just to distinguish. I may not have followed the convention before, but now I try to be restricted. Small m means single division of mass. Capital M is mass matrix. Okay, so we have mass matrix. This nu now has two kinds of indices. It has the flavor index and it has a spinner index. So if I go to three flavors, this generalizes to this MM becomes a mass matrix. So it has indices ij. These are flavor indices. E mu tau.
Number M of electron plus mu of electron.
In general, they can be mixing, but you know they mix. No? If we electron, mu and tau have separate masses, they will not mix, but we know they mix. It has to be a matrix.
So if INJ were mass against it, then you would get a diagonal element.
Yes, the mass against it will diagonal. In general, you have something with ij, and then depending on whether you are in mass or flavor basis. In the flavor basis, definitely we mix matrix. Nu will have two indices. One is flavor and one is spinner. So basically, just like this is a spinner index P and the flavor index is I. C dagger is just a spinner index. Okay? It's a combination of gamma matrices. So I, gamma, 2, gamma, 0 kind of. Nowhere there is a flavor index. So C dagger is just something is spinner index. And again, this nu has two indices. This flavor index J has got it. So everyone agrees that Lagrangian will look like this. Right? Now, try to interchange I and J and see what happens.
Then that dagger will become QP.
Interchange I and J indices. But actually nothing here. This is interchange I and J indices. Call J as I, call I and J. They are W indices, right? They are summed over I and J. So what happens? This MM, what does this become? MMJI. This is mu JP, this PQ and this is JP. So what has happened is MM has interchanged its indices. But everything else has stayed the same. Okay, so because this goes in. So what this means is that if I interchange indices I and J, nothing changes. Okay. The reason basically is you have got both mu here and I and J. So Mij is equal to Mji. So this tells you that the Majorana mass matrix is always symmetric. So all this was basically to make this particular statement. The MM matrix will always be symmetric, okay, not Hermitian. It is interchange Ij. We did not take any complex conjugate efficient. Just written in the match. So the mass, the mass matrix MM is always a symmetric mass matrix. So that's very important. Carry it through. Normally what people do is, we don't even write these Spinor indices. We just assume that they are somewhere. So usually you write down this Lagrangian term like this. You write this as nu. So forget about P and Q. So you know the C diagonal is not required. Something happens. So it's nu I, mmij times nu j. And you write it as nu transpose mm nu. So you agree that this is a short form for this. Exact short form. No cheating, no approximations. So normally therefore you would find that very often people write the Majorana mass matrix in the basis of nu transpose and nu. Remember, this transpose is different from this transpose. This transpose was in Spinor space. This is in Flavor space. Okay, so the Majorana mass matrix in L was nu transpose mm nu. It basically means this nu transpose is nu e, nu mu, nu tau. This mm is this 3x3 matrix, and my nu is nu. So Lagrangian has this term. Lagrangian has this. No bars. Okay, they just nu tau. Because these nu they have no Spinor indices. I already suppressed it. Ideally, each of them is a Spinor. Okay, but in our calculations we don't need that. There is the Spinor degree of whatever they suppress. Therefore, now there are no bars. Each of them are just numbers or functions. Okay, and this 3x3 matrix which equals as MM. So very often you just write this MM matrix as between nu transpose and nu. It's a very convenient way of writing, because then now we have got no conjugates, no bars, no C diagrams, nothing. Just transpose and nu. This makes it clear that this is a symmetric matrix. It's nu transpose M nu. If you transpose it, it should become the same matrix. So it has to be symmetric. So that is the main lesson of today, is that Majorana matrix is always symmetric. Dirac matrix, there is no such condition. So you can't write Dirac in this form. It's always nu n bar nu r. Right? And AR can be Dirac mass matrix can be anything. Okay. Majorana mass matrix has to be symmetric. So now we go to our old Seesaw. So remember that when we saw Seesaw type 1, we saw that the Lagrangian was something like this. So I had mu n bar, mu 1 c bar, then I had 0, mb, nt, bar, and I had mu c. This was the matrix that we got from Seesaw. Because there was no mu n term, there was a Dirac term, and there was a mr. So recall this thing. So at that time, mu n was just electron neutrino, only one thing. So then these would look simply like numbers. Now we want to put in 3 flavors. So what does this mean? This means that instead of writing this nu n, let me come to our newer thing, which was I suppress all the Dirac indices, so I get nu n. It's stable. So this nu n will now not be a single neutrino but three neutrinos. So there will be three of them. So ideally I would have to write them as mu e bar, mu bar, mu term. And mu rc, depending on how many mu r's I have, I'd like to write some mu r1, c bar, mu r2, c bar, so I don't know how many mu r's. You can call them mu e mu, but see, there is no connection a priori between some mu r and this selector. In principle, for example, if I tell you there are 5 mu r's, there is nothing prevent you from doing it. There need not be one mu r per flavor, because it doesn't need to be. Mu r is external completely. So therefore, in general, you don't call it mu r, mu r, you just call it mu r. But then, therefore, these are not just 2, but this will be 3 normal neutrinos plus some n number of right neutrinos. So this matrix does not have 2 components, but 3 plus n components. This is 3 plus n kind of. Similarly, this one is 3 and n. Then this MR is going to be an n by n matrix. So it combines this mu r and this mu r. This MD is, what are the dimensions of this MD? Three cross n. And 3 rows and columns. This matrix would be n cross 3. And just one subtlety, remember that this is a symmetric matrix. So for numbers we just wrote MD and MD, but if the symmetric matrix, this actually will be a MD transpose. And this 0 is now not a number, but a dimension of 0? 3 cross 3.
Why would it be done?
Has to be symmetric. No, Dirac matrix is not symmetric. This is Dirac matrix. What appears here is MD. What appears here has to be MD transpose.
Okay.
Because Varada matrix is symmetric. Internally, it is
Instead of numbers, we are making it matrices.
So it's the transpose of this. So this is what I have written. So this mu n bar is therefore a 1 by 3 matrix. This is 1 by n. Components is 3 by 3, 3 by n, n by 3, MD transpose, and MR is n by n. Okay. So whatever we had written in terms of numbers, we write as matrices. And normally we don't write down the dimensions of matrices. So simply speaking, effective mass looks like this: 0, MD, MD transpose, and MR. Okay, I just made in capital M to remind us that these are for 3. So, just by looking at this, doesn't look very different from what we had earlier. Just that we have to be careful about the transpose. So, this is therefore 3 by n plus 3 by n. Sorry, 3 plus n plus 3 plus n. So, this is not our Neutrino mass matrix yet. Neutrino mass matrix has to be 3 by 3. We have 3. Neutrino mass matrix is a part of this matrix. So let's see how to get to neutrino mass matrix from this big matrix. So first thing that we always do when we look at matrixization mix is we diagonalize. So we diagonalize this matrix. But we don't try to do the whole diagonalizing thing at once. What do? We first block diagonalize. So what we do is we try to find a matrix U, unitary matrix, such that U transpose MU is a block diagonal matrix. This MB reminds you that it is block diagonal. What does black diagonal mean? It has a 3 by 3 diagonal component here. There is an n by n diagonal component here, and these two are 0. So M1 is not diagonal matrix. M1 can have off diagonal element. But log diagonalization means that this and this is 0. So what have we done? We have separated out the active neutrinos, E mu tau, from the so-called heavy neutrinos. So M1 gives you masses of active neutrinos, and M2 gives you masses of heavy neutrinos. This is exactly what we did for Seesaw, except that numbers are being replaced by matrices. Okay. And then what we actually measure at experiments are properties of M1, because M2 are very heavy, M2 are heavy. So they have masses of some 10 power 10 kg or so. You will never see them. So after block diagonalization, we see M1, and M1 is what we are going to observe. So in the context of Seesaw, when I say we look at Neutrino mass matrix, we look at M1. Now, our Seesaw mass formula. Seesaw mass told us that M1 was equal to minus MT squared by M1. This one is Seesaw. When we come to the matrix level, this changes to MD transpose MR inverse MD. So we can write here again. Minus MD squared by. So now that we deal with matrices, matrices don't commute, so we have to be very careful about what is ordering. And ordering is this MD transpose MR inverse MD. You are going to get a big assignment problem in which we try to calculate this. Mixing angle. What is the mixing angle in Seesaw? And this mixing matrix in front of us. So mixing angle theta was MD by MR. Now you will also get something like mixing angle, because now the big matrices get something like MD MR inverse. But you will calculate the exact expressions in your assignment. It's a straightforward thing to do, just in those sort of algebra. So the Seesaw formula, therefore, we generalize to M1 is equal to minus MD transpose MR inverse MD. Okay. So what does this mean? See, normally we know that MR is very heavy, much heavier than MD. That's not 10 part very heavy. MD is very small. This means that in general, the neutrino masses that you will get are very, very small. If all these three MRs are very, very heavy, okay, you will get hierarchical neutrino masses in general. So this is rule of thumb, not an exact statement, but it essentially means that all your masses are going to be very, very small. There is nothing that you have to be. So we know that neutrino masses can be, the lowest mass can either be 0, or all three masses can be close together. So normally type 1 Seesaw will tell you that lowest mass is very close to 0. Because these MRs are often hierarchical. So MR has no restriction. So if I tell you, give me 3 masses for MR. So one of you will give you 10 power 10, one will give 10 power 11, one gives 10 power 10. No one will give 10 to the power minus 11.35, 10 to the power minus 11.37. So usually, if you randomly throw dice and find out what MR masses are, in general they will be very far up hierarchy. So one MR is 10 power 10, second will be 10 times that. At least, something like that. So therefore, since this M1 depends on 1 by M1, if you look at right neutrino masses, the masses will be have factors of at least 10. It's a vague argument, but it's an intuitive way of saying that this thing. So let me perhaps. Let's say there is no mixing. Forget about mixing. So then what happens? You have got md squared by, so m of electron is md squared by m1, m of neon is md squared by m2, and m of tau is md squared by m2. And normally what you would expect is these three will be far apart because they are really very heavy, they can be anywhere they want. So let's say M0 will be 10 times M1, which would mean that Me is 10 times lighter than M1 heavy. So this tells you in general the masses of Me, Mu and M tau will not be close together, they will be far apart. So then you have 0, some M1 is very close to this, some M2 is here. That's what you normally predict. If this is 0, if this 0 was here and M1 was here, then all these three will be close to it. But that doesn't happen with time masses. If this happens, then the M2 mass will be like 10% more than M1, which is normally doesn't happen. Okay, because mass is given by md square by m. Take argument, but you hear people talking, giving these arguments in the talks. Sometimes the concrete thing is that M1 is given by this particular.
Mostly normal, what we call normal inverted hierarchy, talking about that.
Yeah. So okay. So let me. So that's basically what I did. So this is normal hierarchy. It's also normal mass order. It's both. Yeah. Inverted hierarchy is never hierarchy. Inverted hierarchy. So okay. So let me. Since we're going to come to it anyway. So there is. So I talk about. I'll try to be very clear. So I want what's called a normal mass ordering, which basically means I have M1 lightest, M2 and M2. And there is inverted mass ordering. Which means that M3 is the lightest, and M1 and M2 are here. But now M1 and M2 have to be close together because this difference is delta m square so long. So these are, strictly speaking, this should be called as mass ordering. But people also call them as hierarchies. Standard notation, you can't do anything with it. Another concept people use for hierarchy is the following. So let's talk about hierarchy. You can have either normal or inverted. But now, 0 can be here. If 0 of mass is here, then it's possible to have this mass, this M2, 10 times M1, and M3 is 100 times M2. These are called as hierarchical masses. So, this therefore is strictly speaking called as normal hierarchy. Hierarchical normal ordering is normal hierarchy. Hierarchical inverted ordering is also called inverted hierarchy. Inverted, so this means this is some mass M1, then M2 can be 10 times M1. I'm sorry, same thing. So M1 and M2. M1 can be 10 times M3, but then M2 will also be 10 times M3. So this is called as hierarchical, although not quasi-hierarchical. Quasi-hierarchical inverted order. Quasi-hierarchical because M1 and M2 masses are almost equal. On the other hand, if 0 is here, but your masses are here. Or in 3. Then they are not hierarchical. All these three have to be almost the same. So these are often called as quasi-degenerate. Almost degenerate, but not exact. So the words normal inverted hierarchy, people use loosely. So you have to be careful and see what is the context they want. So here I mean that they give hierarchical neutrino masses. Many models do normal, but they don't need it. This is type 1 system. What is the difference in type 2 Seesaw? So type 1, if you add type 2, what does it mean? Adding type 2 means that you have type 1, so you have this mu R anyway. Okay. But you also have this triplet helix, which gives you mass for your neutrino.
What it shows in the previous modeling, it shows that all the three masses would be near zero. What it shows that all the three masses would be close to
MR is
what it shows that they have measurements. The last.
yeah. So if MR, let's say MD is almost equal. It's a heuristic order. MD is almost equal. If MR on MR to MR is hierarchical, then ME, MB, MB will be hierarchical. Okay. And since there is no restriction on MR1, MR2, MR3, they can be anything you want. Easiest thing is to have the hierarchy. So as I said, if I ask three of you, give me a mass between 100 GeV and 10.15 GeV. And if I take those three masses, most likely they will be hierarchy. Okay. Therefore, this
Choosing MR1, MR2, MR3 such that your M1 is equal.
and I am saying the natural choice for MR1, MR2, MR3 is hierarchy. So this was type 1, and the main thing in type 1 was that there was a 0 in the UL. Because in type 1, UL can't get a Majorana mass. They only get it through mu1. But if you have type 2, then you also get UL anyway. Because you get this triplet helix. So only difference that when you add type 2 is that instead of this 0, you get Mn. Everything else is the same. So this effective mass matrix is Ml, Md, Md transpose Mn. That's the only change there. Then you do exact in the same procedure. So now diagonalize all this M1, all this M2, and then you get your M1. Now that you already have Ml, you get Ml minus Md transpose Mr inverse. So you see some formula. Now, in addition to this Md by Mr inverse, has also Ml. So now what happens? Now if I try to give an argument similar to this, I will say that my M electron, this is type 1 plus 2. M electron is some Ml electron plus Md squared by M. And M of muon is Ml muon plus Md squared by M2. Now see what has happened. I have got Ml already here, and then I have got Md squared by. Now this number is expected to be very small because Mr is very small. So then the main contribution to Md actually comes from Ml. Therefore, if you have type 1 and 2 seesaw both, then you expect that the masses are not hierarchical but quasi-linear. So this is again a heuristic argument. Not an exact argument. This is just some way of trying to see if you observe degenerate masses, it's possible that the mechanism is type 2 positive. If we observe hierarchical masses, it's possible that the mechanism is only time. Since there are no clues for us to connect model with theory, we have to take close to all these rules of thumb. Not only exact, but maybe at some point we will have more information and that's one thing I wanted to check. So I diagonalize M effective by U transpose MU, not by U dagger MU. So people know why I am doing U transpose and not U dagger. It's not real. No one told me that in the real matrix. Normally, when you used to diagonalize matrix using U dagger, right? Three of the quantum mechanics diagonalize U dagger. And diagonalizing using U transpose. I am not saying equivalent. Even this equivalent case, I have to diagonalize by U transpose. Equation is fine. This was true earlier also. This is not time to here, diagonalize using U transpose. Diagonalization. What kind of matrices do you normally diagonalize in quantum mechanics? Hermitian matrices are diagonalized by U dagger. This MM is not Hermitian. What kind of matrix is it? Symmetric matrix. So symmetry matrices are always diagonalized by U transpose. Hermitian matrices are diagonalized by U dagger. So you have to be very careful. And we'll see in about 5 minutes. It's very crucial to understand. So this is something that one should never forget. Symmetric matrix has to be diagonalized. So now we have got this MM. This square of the mass matrix, which in this case is this M1. So we said that now that we have Seesaw, we block diagonalize. We take the 3 by 3 part M1, we throw away this M2 because we won't be able to validate it. And M1 is our mass matrix. We do everything in M1. And for Seesaw it is M1. And any other mechanism, finally you should get a another mass matrix, which is called as MM. So what we will do now is see what to do with MM. So forget everything else that we did in last 15 minutes. Okay, let's just take a 3 by 3 symmetric matrix, which we call as MM. It's a 3 by 3 symmetric matrix, and that's it. Nothing else. Now we want to diagonalize this. How would you diagonalize this? Symmetric matrix. So you transpose it. You have to diagonalize this matrix by using our mixing matrix, which is called as UPMX. So this MN is diagonalized such that U transpose EMNX times this mass matrix times U is a diagonal matrix, which is M1, M2, M3. M1, M2, M3 are real and positive numbers. So that's what is meant by diagonalizing M. This is the mass matrix on global basis. This is a mass matrix in mass basis. So this means that now if I tell you the masses of all the neutrinos, and if I tell you what is my PMNS matrix, you should be able to give me what is my neutrino mass matrix. Okay. So I have this U transpose MNU. So U transpose MNU is equal to my diagonal mass matrix. D, upper D means diagonal. So what will my MN be? What about this? I want to post multiply by something so that this cancels out. So that is multiply diagonal. So this you cancels. What about this guy? From left, by U transpose. What is U transpose? U start. Therefore, once you know what the neutrino masses are, and you know what your mixing matrix is, you do U star MD dagger and you get it. So therefore, now using the data that we measure in the experiment, it's very easy to go back and tell what is the neutrino. So this is exactly what your masses, your mixing matrix. Do you agree? Because you will measure this, but finally, if you want to look at a model, you will need to see what is it. This is one certain point which I want to. Because I used UPMNS in the earlier transformation. But earlier I have told you UPMNS in some other context, like UPMNS of a mixing matrix or neutrino. There we didn't know about Majorana masses. I have to show you that it is indeed the same matrix. Because that UPMNS was diagonalized in the Hamiltonian. You remember that? That UPMNS is to diagonalize Hamiltonian. This UPMNS is something that should diagonalize Majorana matrix. But Majorana matrix is not the same as Hamiltonian. They are different. So I try to show you that the same matrix UPMNS which diagonalizes Majorana mass matrix also diagonalizes. So that's very important. So let's start from the very beginning. You want to write down the effective Hamiltonian in terms of neutrino mass matrix. So we know relativity. We know that effective mass Hamiltonian is E square plus N square root. So this is exactly what I am writing. So I have E square, N square is entire array. E square is also a 3 by 3 matrix now, to the power half. And this is E plus N dagger N by 2p. Simplest, the standard expansion that we did. And then we get N square by 2p, and N square by 2p. Exactly what. So effective Hamiltonian therefore looks like this: M dagger N. P is a number. So M dagger M is what you want to diagonalize. When we say you diagonalize H. So now let's go through these things. So MN is symmetric. This we knew. Therefore, if I do U transpose M U, that is my diagonal matrix, MD. So we have seen this before. look at, see, M diagonal M is Hermitian. Okay, Hermitian conjugate to get the same. Okay. So we should see if the same matrix, if I do a U dagger U on M dagger M, what happens? If it is diagonal, I am safe. If it is not diagonal, then I cannot call both things as UPM. So let's see what happens. So in between MM dagger and MM, I introduce U star U transpose. Okay, which is 1. So here I get U dagger, MM dagger, U star. And here I get U transpose, MM, U. So now look at this. U dagger, M dagger, U star. This is the same as MD transpose. I'm sorry, MD dagger. Or MD star, which you are going to do. Just a star of this or transpose. The second part is just equal to MD. So this is just equal to MD dagger times MD. MD is diagonal, MD dagger is diagonal, so this is diagonal. So what does this mean? I use UPMNS as U transpose U and diagonalize MM. I used same UPMNS, use U dagger U and diagonalize HM. So lesson is, if UPMNS diagonalizes MM like this, U transpose U, it diagonalizes H effective through U dagger. Therefore, we use the same matrix for Majorana masses and for effective. So this is just one certain point. So this is something that you are able to do. So we saw that MM is actually written as U star M U dagger. And you know what U star M U dagger U star. You know what right now U dagger. Right. So I won't spend time on it. This is just for you to check. What's relevant is the following. So MM looks like this. So what does M dagger M do? So finally we want Hamiltonian. So Hamiltonian M dagger M should look like U dagger of MD dagger MD. This way, so from there, so U dagger times M dagger M times U is equal to MD dagger MD. So therefore, if I do U dagger and U, then I get M dagger. Okay. Now I write things down neatly. So MD dagger, sorry, UPMNS looks like this level phases R23, U13, R12, 5. That's my UPMNS. This is my UPMNS dagger. So I go the other way around. So 5, R23, U13, R12, and 5. All phases change sign. So it's a dagger. Now look at this part. MD dagger MD is a diagonal matrix. So what am I doing? I am multiplying on the left by a matrix like this. So I have a diagonal matrix. So M1 square, M2 square, M3 square. MD dagger MD. On this side, I get 5 1 5 2 0. This is e power I 5 1, e power I 5 2, and 1. On the other side, I get the same thing with the minus 5. So I get e power minus I 5 1, e power minus 1. So what is this multiplication giving me? Everything else. I just get M1 square, M2 square, M3 square. So this phi dependence cancels. What does that mean? That means that in M dagger M, there is no dependence on diagonal features. Independent of fiber element. What does that mean? It means that in H effective, there is no dependence on diagonal features. So here, H effective is also true for H effective. What does that mean? That means that in oscillation experiments, there are no dependence on diagonal features. So this makes it sort of clear that in oscillation experiments, you will not have any dependence on diagonal features. So we saw it earlier, we calculated everything cancelled. But this is another way of seeing it. This was sort of such a problem. I'll take about 10 more minutes. So this is just the last part. So what is our aim? Our aim is we have data, we have masses, we have mixing angles. Then we will calculate mass matrices, and looking at the mass matrix, we will try to make some model, some theory, which will give us this mass. So all the theories we saw in the last two classes only give neutral masses. But a job is multifold. You don't give just neutral masses. Neutral masses, but of particular form. Electron neutrino should have mass of particular form. So U1 should be okay. Depending on whether you observe hierarchical masses or degenerate masses, your model should give different predictions. So the aim of model is not just to do neutral masses, but to explain why, for example, the mixing with 2-3 is very high, 45 degrees. You should be able to explain why 1-3 mixing angle is very, very small. So therefore, the final aim is this. Take your masses, take mixings, calculate the mass matrix, and now have a theory which will predict this mass matrix. So that's why we have to go to this step of seeing what is the mass matrix. So this is something that I discussed about just some time back. So for masses, we want to be able to predict eigenvalues. So M1, M2, M3. They should satisfy this because I know what is delta M square solar. I know what is delta M square atmosphere. Then I will measure what is the hierarchy. I may not know now, but I will measure it sometime in future. So my model should be able to give this mass ordering. And it should also be able to tell you whether the hierarchy is normal, inverted, or non-linear. So mass matrix, which is these 9 elements, have to be able to do all these things. So let's see what kind of things we propose. Also mixing angles. No? We know that mixing angles theta 1, 2 is large but not maximal. Theta 2, 3 is 45 degrees and theta 1, 3 is nearly equal to 0. So what people try to do is people try to find some aesthetic solutions, okay? Which means that try to find mass matrices or mixing matrices that look good, can be described in simple numbers. It's some kind of numerology. So if they are simple numbers, then coming up with mass model will be easier. Just believe. So people have come up with many such simple mass matrices, simple mixing matrices over the years. Some of them are the following. There's something called bimaximal mixing. Bimaximal means sin theta 1, 2 is 1 by root 2, so theta 1, 2 is 45 degrees, 2, 3 is 45 degrees, and 1, 3 is 0. So this mass matrix was the most popular mass matrix till about 5 years ago, when we learned that theta 1, 2 is not maximal. Okay, so this is currently rolled. This was popular. It's good for instance. People also had trimaximal mixing, which is sin theta 1 was 1 by root 3. This was 1 by root 3. Third also was 1 by root 3. Okay. But then when we put bounds on theta 1, 3, this got 2. This also got 2. Then people came up with what's called tri-bimaximal mixing. Tri-bi means that theta 1 to sin is 1 by root 3. This is 1 by root 2 and this is 0. This is almost exactly what these three values are. Okay. So although these values are large errors, so not exact values, this is consistent. Okay. So people expect that if the values of 1, 2, 3, and 1, 3 angles are such nice values, then maybe we can come up with good models. People have come up with models with some symmetries, gauge group, blah, blah. But this is sort of one, I would say, popular experiment. Another thing people are talking about is what is called as Quark-lepton complementary. And this means that somehow the signal of quarks and the signal of leptons are connected. So quark angles we know are very, very small. This W angle and then another angle which is very small. Theta 2, 3 is very small. Turns out that one consistent scenario right now is this. So theta 1 to Q is theta 1 to the Prof scenario. The Prof scenario has this CK matrix. Okay. So theta 1, 2 is 45 degrees minus this. Theta 2, 3 is 45 degrees minus this. And theta 1, 3 is this. Happen to fit the data very well. Okay. So people also explore this area. Okay. So I say okay because there's no conclusive proof. It's a good guess. If it works, then people can come up with theories that involve some kind of Quark-lepton probability. Okay, so this is just hope. Right now, yeah, everyone is in some sense hope. So what do we do? Let's say our mixing matrix is this. Type of maximum 1 by root 3, 1 by root 0. I will put in these values in the K-minus matrix. Let's see what I get. So this is my time maximal matrix, which means that I have these phases phi 1, phi 2. My R12, which is theta 12 is arc sine root 1 by 3. Theta 13 is 0. Theta 23 is pi by 4. These are the flavor phases. Okay. This is just convention. Then I get a matrix that looks nice matrix like this. It has 1 by root 2 and 1 by root 6 is 1 by root 3. So it's possible that you get some symmetry that will this. Given this matrix, now I can calculate my Majorana mass matrix. Okay, what does this mean? I do a U star MD U diagram. Then I get a matrix that looks like this. Don't go into details. Each one of them is some combination of masses and Majorana masses. That's not important. What is relevant is, see, if you look at this matrix, it has some symmetries. You see that this element is the same as this element. You will see that this element is the same as this element. Okay. So these two are equal. These two are equal. It is symmetric. So I did not write here because this is also the same as B. Symmetric. This is the same as B. This is the same as this. But that's not surprising. Symmetry is not surprising. What's surprising is that this element is the same as this element, and this element is the same as this element. So what does this mean? This tells me that if my mixing is time by maximal, okay, then I get these characteristics in the mixing matrix. Okay. So what does this mean? This means this is an E mu element, it's an E tau element. Okay. So it means, oh, okay, perhaps my symmetry should be such that mu and tau should be symmetric. This is a mu element, this is a tau element. Okay. So okay, fine. So maybe if I just make mu tau symmetric theory, I will get time by maximum. It's possible. So that's the kind of things you do. Try to think of nice things which will make you some symmetry. So I'll just before leaving give you two simple symmetries. So this was the symmetry we talked about. So mu tau exchange. Which means that if I replace mu by tau, matrix does not change. It's a guess. It's a good guess. And the question is, does the guess agree with whatever we have? So the matrix then looks like this. There is ME, ME mu, and ME tau. But mu and tau is the same. So I don't write tau at all. There is ME mu, M mu mu, M mu tau. But that doesn't matter. M mu tau is the same as M mu tau. Anyway, this is symmetry. And then this M tau tau is the same as M mu. So in this matrix, you will see that you replace all mu's by taus, your answer does not change. So this matrix is what I call as the mu tau symmetric matrix. It turns out that if you diagonalize this matrix, you will always get theta 2, 3 is 45 degrees and theta 1, 3 is 0. I will give it to you. You will see it for yourself. So matrix has this form, which is mu tau symmetric. You will always get theta 2, 3 is 45, theta 1, 3 is 0. So therefore, if you come up with a theory which is completely mu tau symmetric, very naturally you will get that theta 2, 3 reasonable is 0 and theta 1, 3 is, sorry, theta 2, 3 is 45, theta 1, 3 is 0. All you have to do is worry about theta 1. So you already solved many problems. Another kind of symmetry people think about is, for example, what's called as LE minus L mu minus L tau symmetry. What does this mean? This means that everything term that you have, you calculate LE minus L mu minus L tau. If it is 0, the term is there. If it is not 0, term is not. Just like y, no? What do we do? We used to take y1 plus y2 plus y3. If it is 0, you have the term. If it is not 0, it's not. So similarly, you take LE, L mu, L tau, calculate this number, the electron numbers. For example, take this number. This is EE element. EE means this LE is equal to 1. Wait. 1 plus 1. LE is equal to 2. L mu is 0. L tau is 0. So this is not obeyed. So this is 0. With E mu element, LE is 1. L mu is 1. L tau is 0. So it's obeyed. So this element exists. Similarly, E tau exists. Mu tau actually doesn't exist. I don't know. Sorry. See, because LE is 0, L mu is 1, L tau is 1. So this term is minus 2. So you only get this. So if I instead of add LE plus L mu minus L tau, then that will exist. But now even by this simple kind of symmetry, you get lots of predictions. Okay, so for example, this is also I will ask you to show you. This has 3 nice predictions. This actually shows you that theta 2, 3, okay, so perhaps I wrote this for LE plus LE minus L. So I will correct that. So you can predict a value of theta 2, 3. Okay. You can say that the mass ordering is inverted, and you can say that delta M square solar is zero. You will be able to do this. If I just give this matrix and ask you to prove these 3 things, you will be able to do this. So simple symmetries will give you many predictions. So therefore, that's how you relate some symmetry with predictions for theta. There are no simple rules for doing this. Essentially, you look at this and you use your arguments of trace or determinant and so on. So these are again, these are just very few things. People know about textures. Textures means that the matrix, the mass matrix has some zeros. People call zeros as textures. People do things like they use some extra U1 gauge symmetries, like where U1 Y, there is some U1 X, give some charges. So people use extra discrete symmetries, so some rotation symmetries. So we don't go into. Again, I gave these things to you as words. So people interested in looking at mass matrices can look at these 3 words. Search for them and find them. This will also be there perhaps in block of line. Today we will stop here. Next time onwards we will start presentation.